welcome all of you. So we are studying about phase shifter and how to use it with a potentiometer to measure AC voltages with arbitrary phase angle. So we have seen so far that a phase shifter, you can think it like a pair of coils. So this is one coil and this is another coil, and these two coils carry current which are 90° out of phase. So this I am calling it as IR, and this current I am calling as IB. So we need the angle between IR and IB to be 90°. So IR and IB are 90° out of phase. Then if we have a third coil like this, then if we measure the potential across the two terminals of this third coil, then we will see there is some induced EMF, because the red and the blue coil, they create a rotating magnetic field, and that rotating magnetic field intersects or cuts through this third coil or the secondary coil. Therefore, some EMF is induced, and the phase angle of that EMF can be changed by changing the position of this third coil. So you can rotate this coil in either direction, and by changing its angular position we can change the phase angle of the generated EMF. Now the question is how to get IR and IB 90° out of phase, and we also, that means, need two sources of current. But what we can do, say we will connect, so let me draw the symbolic notation of this phase shifter. Okay, so symbolically we draw them, so like a circle, and then it has two coils. Okay, so say this is this horizontal coil, and this is the vertical coil, the red one. Okay, and this movable coil, we draw it like this. Okay, so we have to supply two currents. Okay, you can call them as so one as IR, one other as IB. Okay, and these two are to be 90° out of phase. How to get that? What we will do is as follows. So we will connect a AC source, say here, okay. So let me also put a rheostat so that we can control the amount of current. And so, and this coil we will also connect to the same source, but this time we will connect it, say, through a variable capacitor and a variable resistance. So the function of this capacitor or this capacitor resistance pair is to control the angle of this current. Okay. So IR is like this EMF divided by the impedance of this circuit, which is this resistance plus this coil will have some inductance, also some resistance. So you divide this resistance and this you divide this EMF with this resistance and this inductance, so we will get IR. Similarly, IB can be obtained by dividing this EMF, if this EMF is E. So divide this EMF with the impedance of this circuit, which is C plus this resistance R, call it R1 and R2, C plus, so j omega C plus, so actually 1 over j omega C plus R2 plus its inductance. So you divide by that total impedance, you will get this current. Now you can change this capacitor, you can change this resistance, thereby you can control both the magnitude of this current as well as the phase angle of this current compared to the phase angle of IR. So we can control the phase angle between the two currents IR and IB by changing this capacitance C. Okay. C, as I mean, you also may need to change R2, and you also have to ensure that the magnitude of these two currents are same, provided that the number of turns of these two coils and the reluctance of the two paths are same. You also need to ensure that then these two currents have same magnitude. So you may also need to vary R1, R2 to ensure that the two currents have same magnitude but phase angle 90 degree. Okay. So you change these impedances, and it's possible by changing it appropriately, you can make sure that these two currents are 90 degree out of phase but with same magnitude. But now I can ask a question. So the question is, how do we know that we have achieved exactly 90 degree phase difference and equal magnitude? Okay. So we are changing this capacitance, these resistances, but how do we know that for what value of these impedances these two currents are at 90 degree angle? So the answer is, we have to do a test. What is that test? So we will measure this voltage. Okay, so we will measure this voltage somehow, maybe with a voltmeter or maybe with something else, but we will measure this voltage for different position of this third coil. So this third coil can rotate, you know. So it has an angular position which we can denote with theta with respect to some position. So what we will do, we will check the value of the secondary voltage. Secondary means this voltage, secondary voltage for different position of the this movable or turnable coil or secondary coil. If the magnitude of the voltage is same for all different positions, different positions means theta, the angular position of this coil, then so that means the desired magnitude of these two coils and the desired phase angle between them is achieved. Okay, so that means the phase angle or phase difference is 90 degree. And they have, of course, required equality of magnitudes. Okay. So, we may need equal magnitude of current, or maybe some I mean, if this, say for example, this turn ratio is not 1:1, then we may need some other ratio of the magnitude of these two currents. Okay. But whatever is the requirement, if we find that the secondary voltage is same, the magnitude of the secondary voltage is same irrespective of the position of this coil, that means the desired condition is achieved. To say it in another word, we can say it like this. Okay. So, this thing I will say very briefly. Okay. So, our goal is to have a rotating magnetic field, perfectly circular rotating magnetic field. So, let us write it loosely, perfectly circular rotating magnetic field. So, what do I mean by that? So, I mean that, so if I draw the magnetic field as a vector at different time, okay, then so this is the magnetic field at some time say t equal to 0, then at say t equal to 45 degree, the magnetic field should be like this. So, the length of this, which denotes the strength or how strong the magnetic field is, should be same, but the direction should be at a 45 degree angle. Then at t equal to 90 degree, okay. So, t equal time 90 degree means actually when the phase angle of the reference current is 90 degree. Okay. Then again this should have same magnitude, but a different angle. So, this is a perfectly circularly rotating magnetic field. So, this is what you want, but it may happen that, okay. So, let me draw the phase shifter again. So, this is the body of the phase shifter. Okay. So, this is the frame of phase shifter. I mean, I did not write it. We may find that say at t equal to 0, the flux is like this. Its magnitude is proportional to this length and it is at this angle. At t equal to 45 degree, we find this say here. Okay, and then at t equal to 90 degree, we find it here. Now its magnitude is smaller than the magnitude of at the time t equal to 0 degree. When can this happen? This is only possible if, so I have actually two coils. So one coil like this. So this is one coil which is creating the magnetic field in the horizontal direction. Okay, so I have this if always. This is one coil, and another coil which is like this. So this coil is horizontal, that means it is creating the field in the vertical direction. Now if the case is that this current, call it IB, and this current is IR, if IR is greater than IB, okay, or stronger than IB, so then of course this field, okay, so at this instant red current is maximum, blue current is 90 degree out of phase, so it is 0. So there is no vertical component of the field, and the field is only created by the red current. Okay, so this field is created by IR only. So this field is created by IR only. Similarly, at this moment red current will be 0, blue current will have its peak. So this field is created by IB only. So the value of this field will depend only on the magnitude of IB, and the value of this field will depend on the magnitude of IR. If IR is stronger than IB, we will have this field smaller than this field. Therefore, you see that the magnetic field, it is rotating, of course it is rotating, but it is not rotating like a circle, so to say, because it is stronger here when it is here and it is weaker here. So this motion possibly we can, to understand, we can possibly draw a ellipse like this, and this means when the field is here it is stronger, and when the field is here it is weaker. Okay, so then the field is elliptically rotating. Okay, so here, so in this case we have circular field, here we have elliptical field. Okay, and what happens if the field is like this? Then the induced EMF in the secondary will depend on the position of the secondary. If for example, if the secondary coil is, so say the secondary coil is like this, or this is the third coil where we measure the EMF. Okay, then the EMF will be, induced EMF will be smaller, induced voltage will be less, so lesser induced voltage. Okay, why? Because sorry, this will be more. And if we have the coil here, then we will have less induced voltage. Why? So you can see that for this position, okay, for this position, the induced EMF in this coil is actually created only by this red coil. The flux of the blue coil is vertical, so it doesn't go through this secondary coil at all. Okay, so for this position, the field is created mainly by the red coil. So voltage is created, voltage is caused by IR mainly only, and here voltage will be is generated or induced or caused by IB only, and IB is weaker, so we will have less induced voltage than this position. Here we will have less induced voltage, here we will have more induced voltage. And if we put the coil like this, say at an angle, then we will have intermediate value of induced voltage. Or let us call it medium induced voltage. So what happens? If we look at the voltage for different position of this coil, if the field is not circular, then we will have different values. So let me just summarize this fact. What we want is a circularly moving field, and a circularly moving field is possible only for equal magnitude of IR and IB. So if IR and IB are equal, field will be circular and the induced EMF in the secondary will be of same magnitude no matter the position of the secondary. But if IR and IB are not equal, field will be elliptical and the induced EMF will depend on the position of the secondary. So we can check whether the induced EMF depends on the position of the secondary. If it does not depend, then we are happy, because that means the field is circular. The two currents are 90° out of phase and also equal in magnitude. So this is the test we have to do. We have to move this coil. So you have to move this coil at different positions and check the induced voltage and make sure the induced voltage is same. If it is not same, then we have to adjust this C R2 R1. So we will change this angle theta, we will measure this voltage, say, so that maybe we will do the test like this, say set theta equal to 0°, measure voltage V, then set theta equal to 90°, measure voltage V. If these two are equal, if these two are not equal, then adjust C R2 R1 to make this equal. If this is equal, okay, then we are happy. Then we may do some more tests to be more satisfied, like we will make theta equal to 45°, measure V. If once again we get the same value of V, we are happy, we are done. That means these two currents are 90° out of phase and are at different magnitude. Okay. Okay. So Now last thing is how to use this phase shifter in a potentiometer. So let me draw the AC potentiometer circuit that we had. So this is the potentiometer wire. Okay, and we have to measure unknown voltage. So let me have this unknown voltage Vx AC. So we connect it like this through a galvanometer. This jockey can move along the wire. Okay, so we can connect it here, and so you also possibly recall that we also need a standard cell for the calibration. So this is standard cell, and then we need the power voltage supply for this wire. So of course we will again need two voltage supplies, one for standardization, which will be a DC, this ammeter is mainly for the calibration or standardization, and this is to ensure that the RMS value of DC current during the standardization is same as the RMS value of the AC current when we connect this to the AC source. Okay. So this is what we have seen yesterday, but now the problem is that if the phase angle of this source and this source are known, if these two are not equal, then we can never get a balance. So what we will do, we will actually connect this source via a phase shifter. So instead of connecting it like this, we will connect schematically. Let me first draw. This is the source, then we will have a phase shifter. So this is a phase shifter, and okay, so you can think the schematic of this like this. Okay, so this is a phase shifter, and the task of this phase shifter is to change the angle of this supply voltage. Okay, so we can change the angle and we can move this jockey together until and unless we get a null. Okay, so during the measurement phase, so what we have to do, so the method is simultaneously adjust the jockey position and the phase angle, this, to get null. So it is like a trial and error method. You have to simultaneously move this jockey and change this phase angle, okay, it's bit practically difficult, two things you have to change together, but that's the process, that's what you have to do. Okay, so you have to change these two things, and practically it's not that difficult. So you have to change these two until and unless you get the balance. And yeah, and one more thing, you have to ensure that this current or this reading is not changing. Okay, so ensuring this current I, so this should not change. I is not changing. Its value should be same as the value which we have got during the standardization or calibration phase when we use this standard cell. Okay. Now, this is the schematic. Okay. Actually, that's mainly all. Maybe for a better understanding, I will just repeat this. By actually drawing the schematic of a better schematic of a phase shifter. So, this schematic. Okay. So, let me put this diagram, I mean this part of the diagram here. Okay. So, this schematic, if we want to make it more practical, more realistic, so let's then do it like this. So, let me first draw the phase shifter. Which has two coils. These two are to be supplied with two 90-degree out of phase currents. So, to control say these two currents, I am putting capacitor and a resistor in one circuit, and then let this be the AC source which drives both this current okay. So, this circuit is complete. Now, complete this circuit. Okay. So, then it is getting the two currents required. You can control these resistances and capacitance to change the angle, and okay, and then this will supply here. So, from the secondary, let us connect one side here and the other side here. Okay. So, that means this is the source which will be driving the current through the main wire of this potentiometer. Now, what we can do is so what we do after calibration, so after standardization, say this current, the reading of this current, say the ammeter reading was equal to I during standardization or after standardization. Standardization or calibration, whatever you call. Okay. Now, we have to make sure that the same current flows when we have switched to the AC supply. Okay. Here also we have switched to the unknown source. Okay, but yeah. But before we actually connect this unknown source, we have to ensure that this has a perfectly rotating magnetic field and the magnitude of the EMF voltage is same for different position or different theta. So for that, what we do, we move the, or we change theta, we move the dial, we change theta to say equal to first 0 degree and then theta equals 90 degree, and adjust this resistance and capacitances, call them R1, R2, C1, and adjust R1, R2, C1, so that this current ammeter reading is again I for all values of theta. So that the ammeter reading is equal to I for all values of theta, like theta equal to 0 degree, 90 degree, etc. And once that is done, then we can move, then we can first connect this key to this switch to this unknown source and adjust this jockey and adjust this angle to get the null. Okay. So this is important. Before we connect the unknown source, we have to ensure that this current is same as I, which was the current we fixed or we got after the calibration, okay, after the standardization. Whatever that current was, we have to maintain that current for all values of theta. So we will check for different values of theta whether this current is constant. If not, we will adjust these values, and when we get this current to be constant for different values of theta, then we can connect the unknown source. So this is how to use the polar potentiometer. Okay. That's it. So if you have any query, you may post in the forum, you can email us. In the next video, we will talk about another potentiometer, coordinate potentiometer, which also measures AC voltage with unknown arbitrary phase angle. Thank you.